Right, so we were at spelling out some thoughts about initial thoughts, let's say, about the criticism we have represented. A second thought about the general situation, let's rather say, is that it is important to make one distinction, and I flagged that already at some point, and here I want to say a little more about this. It is important to keep separate two questions that are sometimes conflated, or that are sometimes viewed to be too close to each other. First is the question of the current, what one might call progressiveness or dynamics in the field. And there is no doubt that the current state of fundamental physics has somewhat reduced hope of imminent theoretical breakthrough or conclusive empirical confirmation of central theories when compared to previous stages of physics, and also when compared to expectations with regard to those theories that were prevalent earlier on. So that is quite clear. And it's also clear that this, for example, is problematic for career prospects of young physicists in the field who need to get jobs based on those prospects. So that's one reason why the number of physicists entering in the field, or the number of physicists also aiming at entering the field, is lower than it used to be, for example, let's say in the 1990s. There is also reduced public presence of the field for that reason, because there are not that many spectacular news about developments in the field. I mean, there still are some, and there is a public presence, but it is lower, let's say, than probably 30 years ago. And there is also reduced overall optimism in the field. So, for those reasons. So it is clear that, let's say, the sentiments associated with the field are less optimistic than that used to be the case some decades ago. Now, one should not conflate this reduced optimism with respect to imminent progress with optimism or assessment of the prospects, the theory's prospects of being viable. And this prospects of being viable, the question whether there are good prospects of those theories to be viable is an entirely different question. It is not clear in general whether there is any connection or a strong connection between slowness of progress and prospects of viability. And that goes exactly in the direction that you were mentioning in the morning. So there may be some connection under certain circumstances, but those connections may be quite questionable under other circumstances. And it is one issue to try to understand, or one task to try to understand to what extent they are separate. And assessing this situation, let's say what one can learn from this, or infer from this consideration quite generally, is that the discrepancy between the lack of progress in the field and the lasting optimism with respect to the theory's viability that one can observe in many of those fields actually, is not as contradictory as it might seem at first glance. So that is an important point. Having said that, so having now made 2 or 3 comments relativizing some of aspects of the criticism we have been presenting, there's still the critical perspective on those theories raises one very important issue. And that issue is whether a potentially unfounded erosion of the canonical view and theory assessment due to the circumstances physicists find themselves in, and due to epistemically unhelpful psychological influence, whether that is a fundamental problem to the field. And what one can say, and what is also beyond doubt, is that psychological and sociological elements do affect the scientific process of theory assessment. And of course, those effects become more problematic in a constellation where whether or not a theory is successful is not then decided a few years later based on empirical testing of that theory. So clearly that's a more pressing issue in the context fundamental physics finds itself in today than in a more canonical context of physical reasoning, let's say. One can also say, more specifically, that groupthink is generally a characteristic of science. So both in dominant and in smaller research programs, there are elements of groupthink. There is no doubt about that. One can also observe, and I will say a little more about this in the upcoming slides, that there are histories of optimism, pessimism, change from a more optimistic to a more pessimistic mood with respect to a theory, that quite strongly suggest that there are epistemically unhelpful sentiments involved in making decisions on the perspective on that theory. So sentiments such as hope, disappointment, and also misrepresenting the significance or the implication, epistemic implication of a reduction of activity in a certain research field. So I want to discuss two examples that we have encountered already several times now: grand unification and low energy supersymmetry. If we look at grand unification is an interesting idea, and it was also mentioned already that it has quite considerable empirical support. Initially, it was considered fascinating and very promising also because there was the expectation that the theory could be confirmed via proton decay. And this was, of course, a highly fascinating perspective because it offered an opportunity to test a theory with a very high, inaccessible characteristic scale based on low energy physics observations. So it is a very specific situation, and it is a very attractive situation. And arguably, that consideration boosted hope in grand unification, and therefore also probably to some extent credence in grand unification in the initial phases. What then happened was that proton decay was not found, and there was considerable disappointment about this, which clearly reduced credence in the hypothesis, even though it's not clear whether a significant reduction of trust in the hypothesis is justified based on these findings, because it was clear from very early on that there were or are models of grand unification, and those are not corner models or very contrived models, but absolutely mainstream models of grand unification that did not predict proton decay to be observable by us. So normally, let's say, if you reduce this hope and disappointment element to it, what you would take this to imply is merely, let's say, a significant but not great reduction of the parameter space or model space that still works. So there is some reduction of credence, of course, always associated with ruling out models, but not a very significant one in a case like that, in particular when initial credence is quite high. Then what happened was that grand unification is a fairly, let's say, it's a confined problem. So it has a specific, there are specific tasks to fully understand what how grand unification works, which models are applicable, and to what extent it is reasonable to think about those models in the absence of any empirical confirmation of any of those. So at some stage, research activity on grand unification quite considerably declined, because there just was not much more to do about it in the absence of empirical confirmation. Now, this decline in activity has nothing whatsoever to do with epistemic significance. It is just the dynamics of theory building that explains it. However, from a slightly more distant observer's perspective, this was interpreted as a reduction in credence in the theory. And this had then kind of a self-reinforcing effect for physicists' understanding of the status of grand unification. So it's clear that there is a lot of psychological and interpretational activity around assessing grand unification that is not doesn't have much relation or much connection to epistemically relevant considerations. That's the case of grand unification. A similar story, yes.
A long time ago, I had a really fascinating conversation with Shelley Glasgow about this in the 70s. And he was saying that he actually very quickly got figured out on the whole thing, not so much because of proton decay, but because there were just so many people coming up with particle models based on larger and ever more exotic group structures. People were working on O11 and SU13 and coming up with huge zoos of families, and people were getting PhDs by analyzing a new group and coming up with all the particles. And he said that he felt like it was just completely out of control, and that there was no real constraint on what was a reasonable group to look at. And so, I mean, do you think any of that? Would you agree with him that was
for a while, and this also then once again declined in the 80s, would be my understanding. In the 70s, in the late 70s, there was a lot of activity in thinking about all sorts of additional group structure beyond the standard model or alternative to the standard model at that time even. And yes, I mean, and plausibly that let's say that has an influence on assessment of the status of grand unification. I'm not entirely sure how he would then think about the fact that started the grand unification program, that the standard model particle spectrum just fits into grand unified representations. I mean, that's a significant observation, I would say. And also the meeting of the gauge couplings, to the extent they do, is a significant observation. And lots of other considerations about alternative group structure don't have any empirical support. So I think there is a very substantial difference between those approaches. Yes?
Okay, on this slide, you are saying that hope and disappointment have no kind of epistemic relevance. From a logical point of view, it is clear, there is no doubt. But indeed, physics is so complex that we have not a clear comprehension on which are the logical relation between the different statements and sentences of physics. and second, hope and disappointment are of expert people. So it is, yes, it is true, but it is not completely true.
Well, I think it's completely true, quite frankly. I think there is just no epistemic significance to thinking that it would be nice to have this effect. There can be epistemic significance to the reasons you have behind this hope that induce expectations that you can find it. Of course, that's the case. So if you look at the Susie case, of course the point that supersymmetry could, if at low energies, solve the naturalness problem, that's a significant point. That is epistemically significant. However, the claim here is not that, it's not that there are no epistemically significant points behind hoping that this will play out. And normally there are those reasons. But the point is that hope exaggerates the significance of those arguments that suggest that supersymmetry would be found. So there is some core to it, epistemically relevant core, that amounts to saying that yes, supersymmetry can play several roles, and one of those roles is to explain naturalness, or to give to increase the plausibility of naturalness, let's say.
Taking consideration the case of the novel prediction, what is novelty? It is partly a psychological concept, in the sense that a theory explains something that is inhomogeneous with respect to the theory itself, that is epistemically more relevant than. So, since it is not completely clear as a logical relation in physics, I think that it is not completely correct to say that this kind of emotion and belief that people have about the situation is not interesting. Yes, you are right. It's good that we cannot ascribe too much epistemological weight. But I don't know.
So with respect to novel, I will come to novel explanation actually, that will play a significant role later on. I think that the significance of novel, there is epistemic significance to novel confirmation, and it's a different case from these issues.
Okay, perhaps it depends from the meaning of hope and...
Yes, yeah. Roughly speaking, of course so given that, as you say, there is a rational core behind that, it is not easy to isolate the element of hope that I would call not epistemically relevant from those other considerations. However, this is presented in light of some recent work we did, I did with James Wells, on trying to assess, and I referred to that already, I mentioned that already yesterday, right? That aims at assessing at providing a Bayesian model of reassessing supersymmetry in light of LHC data. And what one finds, of course, those are very general results that cannot be specified too much in a quantitative way, but what we find is that the change in credence due to the LHC data looks much lower on any of those models we discuss than what one would assign to the common perspective on the issue.
So in disappointment, there is also surprise.
Yes, exactly. So there is, yes, hope and disappointment exaggerate first the optimism and then the pessimism. That's the idea. It does not mean that there is no effect of the data on this. There is, because there has to be some reason why. If we don't find it, and we think we would, then it means that credence is reduced. However, the situation can be a little more complex. And in the case of supersymmetry, as discussed yesterday, it is actually. So the extent to which credence changed seems to be difficult to understand in terms of epistemically significant changes in data. And the suggestion is that hope and disappointment play a role in explaining that. Okay, so those were just two suggestions how one can actually witness psychological aspects or elements in credence generation in theories. The critics of dominant research programs are right, on my view, that psychological elements in theory assessment do play a significant role. One can observe that. In light of what has been said before, it is also correct that trust in some contemporary theories in fundamental physics cannot be explained based on the canonical paradigm of theory assessment, because this is a very rigidly empiricist paradigm, as spelled out. So the question is whether, in light of those two observations, it is plausible to suspect that the main cause of the noticeable shift in the paradigm of theory assessment is psychological. So it's like motivated by considerations such as, hope, groupthink, whatever, and therefore epistemically irrelevant. And that will be the topic of the next session of these lectures. Before getting there, however, I want to offer a general consideration on this. And the general consideration is that, of course, identifying exaggerated trust in empirically unconfirmed theories is important. And there is a risk that this happens that must be taken very seriously. And it is a context of research where this risk is higher than it used to be. So that's clear on the one hand. On the other hand, it is also clear that the scientific paradigm has always been a function of the characteristics of ongoing research. It's not a God-given set of rules that we must follow because of some voice from above. We made up those principles, and we made it up because of our experience with the success rate of those principles also. So it makes no sense to try to freeze them in face of shifting characteristics. To say that this is the way physics has been assessed, or physical theories have been assessed in the mid-20th century, that's the way this has to be done, and we must not change anything about this. That's not a promising attitude, because that was never the attitude in physics. One might add that philosophy of science has contributed something to the idealized understanding of the way science proceeds. Confirmation never worked in the way the canonical view suggests. It always involved meta-empirical elements, and of course there are many philosophers of science who have often emphasized this from very early on. But there is this core idea about empiricist basis for doing science that focuses a lot on this simple system of a theory's prediction and the agreement of that prediction with the empirical data. But the story was never as simple as that. So if one defends that understanding of how science proceeds, one does not even defend the way science proceeds in the 1950s or whenever. It never worked that way. Right? It is an idealized understanding, a simplified understanding of the way science works. So in view of that, the present situation may be less radically different from previous stages of science than it might seem at first glance, which does not mean that it is not different, but it is it is significantly different, but not as radically different as one might think. So, yes, what one can take away from this is that it is important to search for epistemic reasons, to think about epistemic reasons for having trust in the given theories under these circumstances. So to try to understand why scientists do have trust in theories such as string theory and so on under the current circumstances. And that will be the main topic of what comes next. So I now need to shift to the other slide set. So maybe someone can help me with that, and to the day 3. And while this is happening, we might discuss what happened up to this point a little bit. So if there are any comments or questions on that.
So let's say that we have some theory and like a third of the models carry implications that are testable within like foreseeable technological improvements. Then for pragmatic reasons, those will be especially interesting in a sense. So there is like a notion of this being kind of a feedback loop of like enforcing special interest in these things,
Yes.
even though there might not be
Right.
empirical reasons.
Right. That's absolutely right. So there is a distinction between what one may call pursued worthiness in a certain context and credence in the given hypothesis. So it may make sense to work on testing a specific hypothesis just for the reason because that's what one can test, even though one may not think that that's the most probable hypothesis. It is just the one that is testable at this point. And there are other considerations along similar lines. So right. So those are two different questions. Yes.
And I guess that all like comes into it. It would be very nice if one of these
Right. Right, exactly. It is also, yes, I mean, that's a very good point, actually. One may frame this conflation of the two questions as a conflation of pursued worthiness and credence in the hypothesis. So people clearly had good reason to think that that's, at this point, a highly pursuit-worthy enterprise, because it is a very interesting hypothesis, and you can test it empirically. But that's, once again, a different question from the question of credence, yes. Yes.
Oh, my
Please.
question actually, yeah, I would just would you, at least prima facie, what you said in the last slide is very different from the message that Curio is trying to instill in us.
Yes, that sometimes happens.
Yeah, so that's what I want to, I'm glad he raised his hand, I want to hear his feedback.
Well, I wanted to make sure, I strongly feel that like the old folks like me should not speak up during discussion period until students have asked questions. Students should have priority, so are there any student questions?
Not at this point. No.
So I actually wanted to, this is in line with what Yifei requested. I thought it actually might be useful to give a very, very brief rehearsal of the conversation you and I had over lunch. So I thought that that some really nice points were raised. So I'll say what I said to you, and then you can say what you said to me. To me, I completely endorse what you said about the traditional view, and in philosophy of science, and that being that was never how any science works in history. But to me, the really important point is for making contact with the empirical isn't so much being able to, at least in the development of new theories, and really radically new theories, isn't so much that they're able to make testable predictions, but that they have to be developed under the pressure of constraint and guidance by existing empirical data. And in my view, that's how essentially every great theory change in science has happened. The new radical theory was developed, either because there were experiments that just, were really inconsistent with existing theory, or else there were some physical principles that were deeply empirically entrenched, but that current theory had no explanation.
Right,
Something like
right,
that.
yes.
And then, I was pushing you on the fact that in my view, string theory didn't have this. And so I think it might be useful for you to tell me, for you to say what you said in response.
Yes, I mean, this is a great way of introducing this part, I think, because this is exactly about this.
Right.
I would think that it is more effective if I respond to your point in course of presenting this, because that will lead up to exactly that question.
Excellent.
Yes. So yeah, so that's a great starting point for thinking about this. So the starting point is to think about how can it make sense to how can it work that one assesses these constraints or the significance of such constraints. And then we can look at specific theories and think about the ways it plays out in those theories. Yes, but before, let me now change the perspective quite substantially. So what I will be doing now is actually, at least initially, very different from the perspective or the let's say the character of the discussion that I have spelled out up to this point. It is about empirically confirmed theories, and about the question, how does empirical confirmation work at all? Not in cases where there is insufficient empirical evidence, but how can we understand that empirical confirmation actually generates trust in the predictions the theory gives us? And that's what will be addressed by meta-empirical theory assessment. Of course, I should also notice that what I will do now is very close, or is directly what I have been working on for quite some time. So it's also a more personal perspective, let's say. I mean, the previous perspective also had my own views quite strongly built in, but still it was an attempt to represent the character of the debate. So this is an attempt at answering the question, what can be a rational basis for assessing theories, the status of theories in the absence of conclusive empirical confirmation, or maybe any empirical confirmation at all. And I want to start with an interesting episode in recent physics. There is an experiment with neutrinos called the opera experiment. And never mind what exactly they were aiming to do at that point, but what they ended up doing without the intention of doing so was they thought they measured superluminal neutrinos at the speed higher than the speed of light. And they measured that with extremely high significance. So significance that based on which it was completely out of the question that was a statistical fluke. Opera is a highly reputable experiment in 2011, and it is, of course, highly significant that they make that claim. However, no one, next to no one, probably not even the experimenters themselves, really believed in that result. The experimenters thought that the scientific process kind of forces them to make that result public after they had made all the checks and thought that they hadn't made any mistakes. And of course, in case that this played out, it would be a huge discovery. However, there was one very big problem with this, and that problem was that the neutrinos moving at the speed higher than the speed of light, as measured in that experiment, would contradict special relativity. And no one could imagine that special relativity was false in the given context, made wrong predictions in this context, which does not mean, when we come to that there is no context where one might doubt special relativity. But in this context, this was considered to be so carefully checked that this couldn't happen. One must also say that this does not mean that there was no way out for them. So this was not, strictly speaking, inconsistent with previous results. It might have been that, or from their perspective, it might be that there is something very surprising going on that allows for this in this very specific context for some whatever reasons. But no one thought that was a realistic option. And eventually, this skepticism was vindicated. It turned out that there was a problem with the experimental setup, and that had caused the false detection of superluminal neutrinos. So these expectations were correct. Now, the interesting thing, of course, is that under normal circumstances, an opera result would have been taken to be most probably correct. But given the given measurement contradicted a hypothesis that was taken to be next to certainly correct in the given context. So what happened there, what is interesting about this context is that this is about playing two probabilities very high to the value 1 against each other. There is the probability that an opera experiment doesn't make a mistake, which is very high up, I don't know, maybe let's say 99.5%, something of that kind. And then there is the probability that that special relativity is correct in that particular context, and that's maybe, I don't know, 99.999%, something like this. This does not mean, however, that observers had a dogmatic belief that special relativity must be true in this context. So there were, when the experiment came out, the results came out, there was a flurry of papers thinking about ways in which actually this could be right, and in which actually there is some very surprising way in which they were onto something. So it was not the case that it was ruled out entirely. It was really, what happened could only be understood in terms of comparing probabilities to each other, actually. To say that, okay, opera most probably is right under normal circumstances, but the other probability is even much higher. So under these considerations, under these conditions, what happened was that the experiment turned into, in effect, into an experiment about the mistakes made in the experiment. And what was taken to be the outcome of that experiment was, yes, they made a mistake. Then the question was, okay, so what is the mistake? And actually the prediction, so to say, that they made a mistake was then vindicated. They did make a mistake. So let's say the hierarchy between what is tested by the hypothesis or by the experiment and what is the framework assumption within which that plays out got inverted due to this very surprising result. So what that means is that even very high probabilities, very high credence in the reliability of an experiment in a certain context are being taken very seriously. So saying that this probability of special relativity is much, much higher than the probability of them making a mistake, that's a significant element of understanding the status of a scientific theory. So the question then is, on what basis can you be so sure about the theory's predictions? And what it also shows is that there is no deduction, there is no scientific statistics that establishes this high credence. It's a vague kind of consideration, right? It is, of course, if you spell out what it is, you say that, well, there is so much empirical confirmation of special relativity, there is such a dense web of confirmation. It seems very difficult to imagine that there is this loophole here that applies just to this particular case. But that's not a precise analysis. It's a rough estimate. And what is remarkable, or what is maybe counterintuitive even a little bit, is that these vague considerations about the constellation can lead to such a high level of credence in a hypothesis. So now, of course, the problem here is the question to assess the probability of an alternative that is in line with this observed data. So how improbable is it that a theory of that kind exists? And basically the consensus was that it is hugely improbable. So it was what I will later on call a paradigm case of a no alternatives argument. There is no alternative here with respect to the outcome of this experiment to special relativity. And we understand that, we think, well, the physicists' view was that they could be so certain about this that they would just discard the experiment for the time being until maybe if there had been other indications, then that would have changed. But just this one single experiment was not enough to shatter confidence in that no alternatives argument. So, all right. So all this suggests that it is quite interesting and actually quite helpful to take probabilistic reasoning about the status of hypotheses very seriously. It is the only way of making sense of what is going on here. And this is in conflict with a long line of considerations in the philosophy of science that are fairly skeptical of the use of probability. Karl Popper, for example, fully rejected the notion of scientific confirmation because it relied on attributing a probability to a theory. And he thought that just doesn't make sense. And logical empiricists had were, let's say, less dogmatic about this. They were interested in the role of probability, but many of them, for example, Karl Hampel, were quite skeptical of the role of probabilistic reasoning, of the epistemic significance. So logical empiricists would often try to avoid probabilistic reasoning as much as possible. More recent perspectives of confirmation are dominated by Bayesian epistemology, which is explicitly probabilistic. So there has been a quite substantial change in perspective on confirmation and on theory assessment, therefore. So one might think at first glance that Bayesian epistemology, canonical Bayesian epistemology, that is, can handle our two cases. So the case of comparing Einstein theory and the Opera experiment, reliability of the Opera experiment. It turns out that it cannot, and I will now come to argue why it cannot. So this is a little bit about about Bayesian epistemology. Bayesian epistemology is based on the famous Bayes formula, where you have the conditional probability of a hypothesis given some empirical evidence E, so P of H given E. Let me try to find the pointer here. And that equals the probability of the evidence given the hypothesis, which basically is the empirical import of the hypothesis, times the probability of the hypothesis, which is called the prior, so the credence one has in the hypothesis before taking the evidence into account, over the probability of the evidence. And the crucial part in here for our consideration is will be the probability of the evidence. Now, the definition of confirmation is that evidence confirms if the posterior probability of the hypothesis, given the evidence, is higher than the prior probability. Now, it's clear, if we look at this, just a remark on this, if we look at this from the perspective of string theory, that string theory at this point lacks specific empirical confirmation. So no substantial trust in string theory can be generated in a canonical model of confirmation. So that's not yet a problem for the Bayesian account. That one might say that demonstrates that string theory is a speculation. However, if we now apply this model of updating under evidence to the opera case, we also run into problems. And this, of course, is a case of very high level of empirical confirmation. So at first glance, Bayesian epistemology seems to work quite well in the opera case. Special relativity obviously got lots of empirical confirmation, so the posterior credence should have reached, based on this evidence, very high values based on a series of Bayesian updating on those various stages of sets of empirical evidence. So one can therefore establish a plausible framework for claiming, okay, so in this case, it just so happened that special relativity reached this extremely high level of credence. But if we look more closely at the formula, this just doesn't work. And the reason, once again, is this part. It's the probability of the evidence. And this probability of the evidence can be spelled out as the sum over the probability of evidence given some specific hypothesis times the probability of that hypothesis summed over all hypotheses that can account for the empirical situation before taking the evidence E into account. So that's the probability that the empirical evidence E arises. And this includes not just known hypotheses, but also what is called unconceived alternatives. Which means that, of course, I can understand that there is no other hypothesis that we know of that is in agreement with the data. So those hypotheses don't contribute to the probability of the evidence, but they may be unconceived alternatives that do. So the question, if I want to assess the probability, this total probability as it is called, the probability of evidence, is are there unconceived alternatives or not? And which, of course, is exactly corresponds to what we have been saying before. That's the question they have. In saying that Einstein special relativity is most probably the probability very close to 1, an adequate description of that setup, what they say is the probability that there is any alternative that says something different is very low. And that's a statement about unconceived alternatives. So the probability, the posterior probability has the potential to reach high levels, but only if the total probability P of E is very low. In the case of this Einstein discussion, extremely low, and that means only if they basically rule out the existence of unconceived alternatives. That's what they need to do. And canonical Bayesianism does not offer any basis for doing that. So it provides no basis for explaining credence in a theory because it provides no basis for assessing P of E. All it can do is it can state it. It can represent it, let's say, but it does not offer any process based on which one can arrive at this conclusion. And all this emphasis on empirical data that has been introduced does not help, because it's not in the end about the agreement between the data and the predictions of the hypothesis we have. It is about the question whether it is reasonable to expect that there is another theory that also predicts this, or that predicts something different, let's say. So this question is crucial, but it's not about this strict comparison between a theory's predictions and the empirical data. It's an assessment about the spectrum of unconceived alternatives. And now the Bayesian can say, okay, in this case, let me put this probability basically to 0, the probability of unconceived alternatives, but I don't tell you why. It's just that's what scientists happen to think in this context. So only on that, on this tuning of their initial credences, based on tuning these credences, they can explain what happens there. Or it means they cannot explain it, they can just represent it. So the question is, can one do better than this? Is there a way of assessing how many unconceived alternatives there are that predict the evidence? And the problem with this is that in order to do so, one clearly cannot rely on the evidence, on the implication of the theory, on the evidence in the theory's intended domain. Because evidence in the theory's intended domain just, again, opens up the very same questions. There can be other theories that predict it, but they may not be. So the evidence itself that can be predicted by the hypothesis cannot answer this question. So we need to do something else, and the suggestion here is meta-empirical theory assessment. And this is an assessment of the spectrum of unconceived alternatives based on observations that don't lie in the intended domain of the theory. So this is not strictly empirical confirmation, but it is about observing some other stuff, some other contextual information, getting contextual information about the research process mostly, that can allow us to assess the spectrum of unconceived alternatives. So the idea is that we need to shift to a meta level in order to address that question. And shifting to this meta level means to go beyond a canonical understanding of Bayesian epistemology that focuses on the empirical data within the theory's intended domain. So what we need there is evidence that is meta-empirical in the sense that it is not in the theory's intended domain, but it's not just an observation about the theory itself, because we want to learn about this. We want to make observations that tell us. We want to look into the world and learn something from looking into the world about this situation. So, for example, if we look at a track record of scientific success, that is looking into the world and seeing how our theories play out. So it's not just saying that a theory, to go back to this elegance and beauty story, it's not just about saying a theory is beautiful and therefore I increase the prior. It is about observations, genuine observations, but observations that are not in the theory's intended domain. So it is this F. So I call E evidence in the theory's intended domain, and I call F observations that lie outside the theory's intended domain, but they are still observations.
What is PP?
Sorry?
What is PP? There's a gray arrow with PP.
Oh, the PP. Why did I write PP here? I don't know, I must say. So I don't know what this PP stands for, actually.
You gotta stop smoking so
So it is what this arrow implies is that the evidence is in the intended domain of the hypothesis. That's why the arrow is there. I don't know where this PP comes from. All right. So there is a second requirement. So the first requirement is that this needs to be empirical evidence. It is empirical evidence outside the intended domain. The second requirement, if we think about ways of handling this, is that we want to have a kind of, to remain as close to the setup of empirical confirmation as possible here. So the idea is to resemble a process of empirical theory assessment to the extent that can work at all. So if we think about the setup in the case of empirical confirmation, we have a hypothesis that predicts the data, and then we have data that is in agreement with that predictions. So we would want to have something comparable at the meta level. And having something comparable means that the hypothesis I have at the meta level is not the theory itself, but it is a hypothesis about the spectrum of unconceived alternatives. So the hypothesis as to how many, if any, unconceived alternatives exist. So in this opera case, the hypothesis is there is a very high probability that none exists. Now, I need to find observations that are actually predicted by that hypothesis. So the question is, what can be predicted by the hypothesis that there are no alternatives to this? In order to be a little more specific about what I mean by alternatives to the hypothesis, I need to think a little bit about scientific underdetermination. So why here would be the hypothesis about the number of unconceived alternatives? This is associated to underdetermination, scientific underdetermination, as I call it in this context. And scientific underdetermination then amounts to the statement that empirical data allows for a spectrum of scientific theories with conflicting empirical predictions. So the important point here is that those theories under discussion are empirically distinguishable, because only that empirical distinguishability makes this an empirical issue, right? If I discuss empirically entirely equivalent theories, I will never get information about this based on meta-empirical observations. So I need to be able to find out in the end, in cases where I test the progression of predictive success, whether other theories actually showed up. Now I can distinguish between two ways of discussing this. I can specify what one may call an empirical and experimental horizon, and just look at scientific underdetermination within that horizon. So I have a localized research question. I ask, for example, the question in the opera case, how probable is it that in this is a very specific case, and that's why the probabilities is so extremely high also. How probable is it that in this specific empirical setup, there is a theory that gives predictions that differ from the predictions of special relativity? So that would be a classical case of a local scientific underdetermination question. One might also have a global question and saying what is the probability that there are any deviations at all? So with respect to special relativity, that would be the question, how probable it is that there are any theories that disagree with predictions of special relativity anywhere in any data set we could imagine. And of course, such a question is notoriously difficult to answer. So that would not, global questions would not be the first choice in thinking about meta-empirical assessment. So meta-empirical assessment would always be, if effective, would always be localized, focusing on a specific domain and asking the question, how reliable is the theory in that domain? So then limitations to scientific underdetermination would amount to saying that the spectrum of alternatives is very small. In the extreme case, there are no alternatives. Okay, so here are three arguments, three types of observations that work along the lines just spelled out. So those are observations that can be predicted by the hypothesis that there are very few or no alternatives. So let's take the extreme case. Let's take the hypothesis there are no alternatives. If there are no alternatives to the given theory in the given domain, empirically distinguishable alternatives, that is, then one prediction is that scientists won't find any, because if there are none, they can't find them. A second prediction with respect to a wider research context would be that if there is a research context where this situation is widespread, where the situation that there are no alternatives to a given theory is often arises, or tends to arise, let's say, you would often find contexts where theories are predictively successful if one has come to the conclusion that there are no alternatives. That would be the meta-inductive argument, the third argument. The second argument, unexpected explanation, amounts to saying that if there are no alternatives to a given theory in a wider context, so that would not now apply to this specific case, because to the case of the opera experiment, but if we assume, if you ask the question about a wider domain of phenomena, and the hypothesis is, with respect to this, this domain, with regard to several of those research questions, there just are no alternative ways to explain the data other than the theory at hand. If that's the case, then we would expect that one and the same theory can explain several different things. So it can, in an unexpected way, show explanatory interconnections between specific characteristics. While if I assume, go to the other extreme and think that there is an abundance of solutions to each of those problems in that domain, there is no good reason to expect that the solution that can be that I happen to find with respect to one specific problem also works for another problem. Because this wide range of solutions may not overlap that much. There is no reason for me to expect that they overlap. So the prediction coming from the hypothesis that there are no alternatives with respect to theories in that domain implies that I find cases or predicts that I should find cases of unexpected explanation, which I would not find to the same extent if there is a vast range of options. So that means that those three observations, meta-level observations, are all of those, that all three observations are related to the hypothesis that there are very few alternatives or none at all. And that turns these observations into, at the meta level, into observations that increase credence in this hypothesis. In the hypothesis that there are no alternatives, or in the hypothesis that there are very few alternatives. And of course, if one would formulate that more precisely in a Bayesian framework, one would need to sum over all this Y hypothesis with respect to a certain number of alternatives. But that's just the formal model based on which one can do that. So that's the basic idea. So let me ask you whether, whether this was roughly clear, whether there are questions or comments on what has happened so far.
Are you going to give an example of everything you said on this page?
Yes, I will.
Okay.
Yes.
If I'm talking too much, just tell me, just shut me down. But I didn't really follow the unexpected explanation part. It's not, I didn't follow one that somehow is concordant with no alternatives. You said, well, if there are many alternatives, then there's no reason to think that, that the rest of them will give the explanation for the unexpected thing that this one did. But as far as I can see, there's also no reason to think that they won't.
Right. I mean, it is not a wide range of explanations does not exclude that you find them, but on that basis you don't expect to find them. If you think about, let's say, if you think about questions in a scientific domain that seemingly have not much connection to each other, and you want to model explanations of that specific phenomenon. And now you look at one and you have the understanding there are lots of ways of modeling this, right? We have, the data is not very good, let's say it's a very rough data, so I can come up with all sorts of models that explains this one thing. I come up with all sorts of models that explains an entirely different thing. Now the question is how likely it is that the model that I apply to this one context that is tuned by me in order to provide an explanation of this specific context, how probable is it that this will also work in this other case? And one would say, well, it's not probable. Why should it? I have all those options, and I don't expect that there is a universal applicability of each of those models. Why? Because I just developed them to solve this one problem rather than the others. If I, however, assume that I'm dealing with universal theories of that domain, so the theories are all those phenomena are in principle in the intended domain of my theory, and then I say, okay, I assume now that there is just one possible theory that can account for the data that's already in. So there is no other way of accounting for that data. If that's the situation, I must expect that this theory will be able to predict, explain any question I have in that domain, because there just is no other theory. So that's the basic reasoning. And of course, observationally or technically, I come from the other side. I observe this unexpected explanation pattern, and one would argue then that such a strong pattern, if there is a strong pattern, that a strong pattern of unexpected explanation suggests substantial constraints on the spectrum of possible alternatives. That's the line of reasoning. Okay, so let's look at the individual observations or the individual arguments step by step. One would start with the no alternatives argument, because the no alternatives argument is a direct statement about the scientific understanding regarding the spectrum of alternatives. So it's the starting point, because one, in order to have credence in a given hypothesis, one needs to at least be able to think, to say that at this point there are no plausible alternatives to this individual hypothesis. So the observation then, however, of course, is only that scientists haven't found them. The observation is not that there aren't any, because one doesn't have access to this question. Which means that this observation that scientists haven't found any alternatives can be due to the fact that there are no or very few alternatives, but it can also be due to the fact that scientists just haven't been clever enough to come up with those alternatives. So on its own, an alternatives argument in isolation is not a strong argument. It is a starting point for meta-empirical assessment, but on its own it has very little empirical epistemic significance. One needs to establish the significance of an alternatives argument based on other means. And one strategy that plays a very important role in science on this account is the strategy of emphasizing or registering cases of novel confirmation. So novel confirmation, of course, there is a long-standing debate on whether or not novel confirmation is epistemically significant and has confirmation extra value over accommodation. This is a long-standing debate, and there is a traditional Bayesian answer, and this traditional Bayesian answer is no. There is no basis for making that distinction, because if you just look at the import of evidence in the intended domain on the probability of the hypothesis, there is no leeway to account for novel confirmation. Now, there have been discussions within the framework of Bayesian epistemology that suggested otherwise, and I don't want to go into those. They are related to the perspective I want to suggest here. What I just want to say is that on the basis or within the framework of meta-empirical assessment, novel confirmation does have epistemic extra value, and it does have epistemic extra value because it can be characterized as a case of unexpected explanation. So it is a case where what we have just discussed before, where this observation that if there were lots of theories that that give different predictions with respect to various phenomena, I shouldn't expect that the theory that I have tuned in order to get one observation right should also give the correct prediction with respect to another observation. So exactly that line of reasoning directly applies to the novel confirmation case, right? So the idea would be, if I spell it out in detail once again, if I have two data sets, let's say, and I have a theory that I develop in order to account for one data set. And now I ask the question, okay, there is also this other data set. I haven't collected that data yet. It's in a different context and so on. So how likely is it that the theory I have developed in order to account for this data set will also correctly predict the other one? And on the meta-empirical assessment line of reasoning, one would say, well, if there is an abundance of options to account for this data set, and these various options vary in their implications with respect to the outcome of the other data, there is no good reason to expect that it will be on the right track or will provide the correct data in that other case as well. However, if I think there is just one theory in this domain that can be built, then of course I will expect that it will also be give the correct data in this other case. So that's the way one would read novel confirmation within the framework of meta-empirical assessment. So it's a particularly straightforward, the most straightforward case of unexpected explanation. Another context that is very helpful for gauging the significance of an alternatives argument is the meta-inductive argument. The meta-inductive argument assesses the significance of the no alternatives argument based on checking its success rate in the field. So the idea is, if I work in a field where no alternatives arguments have already been put forward previously, and in that field, in most cases when they were put forward and then the theory could be tested, the predictions turned out to be correct, that suggests that the no alternatives, the reliability, that the assessment that there are no alternatives based on no alternatives having been found is kind of reliable. So it suggests that the scientists work in a field where they can quite well exhaust the spectrum of possibilities. On the other hand, if that's not the case, if scientists make the claim or announce that they haven't found alternatives, decide looking for alternatives for a long period of time, but then whenever they test their hypothesis, it turns out that the predictions are wrong, then of course they need to continue searching for those alternatives, and probably eventually they will find them. So if they are in a situation like that, a meta-inductive argument would suggest that no alternatives arguments are not particularly significant epistemically. So meta-induction works very well in conjunction with an alternatives argument because it directly goes against the alternative explanation of the no alternatives observation. The alternative explanation is that scientists are just not capable of enough to find those alternatives, but if their track record of success once they have announced no alternative claims is that most of the time they turned out to be probably right, then that suggests that their assessment of an alternative cases is quite reliable. So that is the structure of this reasoning. And now, if one tries to understand the status of those individual arguments, the starting point, as said, is the observation that scientists haven't found alternatives. And then from there, they move, one can move towards assessing novel predictive success within the same theory. They can move beyond the same theory and focus on the track record of success in the given research field. And they can also move in these other directions where they don't focus on novel predictive success or novel prediction, but they focus on unexpected explanation in a more general sense. And this will be important for us, because novel predictive success, of course, is a very nice element of meta-empirical assessment, as long as there is empirical confirmation of the theory. But in cases where there is insufficient or maybe even no empirical confirmation of the theory at all, it just doesn't apply, right? If there is no empirical confirmation, there cannot be novel predictive success either with respect to that theory. So in that case, one needs to move away from this core consideration, and one can either move towards the entire research field, in which case one ends up discussing meta-empirical assessment, meta-inductive theory assessment, sorry, and the meta-inductive argument. Or one can move from novel predictive success to a more general characterization of unexpected explanation. And I will give an example in the context of string theory of such unexpected explanation later on. So that's, of course, what would be required in a context like string theory, where this blue part is just not accessible. So you don't get meta-empirical assessment from here in the case of an empirically unconfirmed theory. And that's the reason why meta-empirical assessment can never be as reliable in cases where there is a lack of empirical evidence than in cases where there is lots of it. So another way of viewing this is in terms of constraints on the spectrum of possible theories. And that now comes back to Eric's question. If one tries to find alternatives based on a set of empirical data, the stronger and more varied this empirical data is, the more difficult it becomes to find theories that actually account for all that data. So if, let's assume that there is a situation where there are already suspicions of a scarcity of unconceived alternatives, and so there is a kind of, let's say, a weak no alternatives case to be made. And what then happens is that there is a succession of empirical confirmation that makes it ever more difficult to think about possible alternatives. That makes the no alternatives case, of course, much stronger. So this process of additional constraints, be they conceptual or be they empirical, collecting those constraints and acknowledging those constraints increases the epistemic significance of meta-empirical reasoning. And clearly, if there is if there is very strong empirical confirmation and there is a strong case of novel confirmation that can be extracted from the empirical success record of the theory, that would be the optimal case for making a strong no alternatives case, a strong meta-empirical assessment that eventually now can lead to extremely high credence in the hypothesis or in the predictions of a hypothesis in a given domain. So that would then be the process. One now moves back to the opera case that can lead, based on these meta-level consideration, towards an extremely high credence in a hypothesis such as special relativity. And once again, I think the important point to make is that even though all this looks vague, it is vague reasoning. There are no experiments to be made, no actual statistics to be applied at this meta level. So it is vague reasoning, unlike statistical data analysis at the ground level, where one can make predictions. Nevertheless, the extremely high reliance on these considerations is the only way to exclude the option of unconceived alternatives. So it is needed in order to have a very high credence in a hypothesis. The flawless, strong statistics based on data collection at the ground level on its own just is not enough. That is, so to say, the upshot of all this.
What is the y-axis of the two-dimension graph?
Going upwards.
Yeah, going upwards. Does it mean that we should move to research physicists?
So the idea would be that it is always helpful to move that way, because it gives additional support to the case. So the problem with just relying on the same theory is that the meta-empirical data set will be quite constrained, right? You will have several cases maybe of novel predictive success in the theory, so that's already significant. But you may want to have a better understanding of the entire research field, so better understanding of the way in which successful predictions and a novel confirmation case actually can support a no alternatives hypothesis and can establish that it is very likely that the theory will be predictively successful. And you have much more data if you move up this way and look at the meta-inductive argument as well. So this is even in the case of if there is a lot of empirical data, empirical testing of the given theory, this meta-inductive argument will always play an important role. The moving in this direction may play a role, but may not be all that significant if there is a strong case of empirical, of novel confirmation already. So if there, in case of strong levels of empirical confirmation, that would be the preferred line of reasoning here. So no alternatives observation, novel prediction, and the meta-empirical argument that points at the high success rate in the research field, saying that, look, we work in a field where theories that are considered to be without alternatives have a very high success rate.
Sorry, you may have already explained this, but I didn't understand why the unexpected explanation is to the right, like why is less important than novel prediction?
Well, it is a more difficult. Sorry, it is more difficult to come up with conceptual interconnections that are separated from empirical testing if there is lots of empirical testing, right? So most often you would be able to spell out the problem in terms of an empirically testable problem. And once that's the case, you would actually move there. You can spell out what you're investigating in terms of novel predictions. Only if you're not if you don't have empirical testing of the theory at all, you need to focus on contexts where there is nevertheless explanatory interconnection. And yes, and as we will see in string theory, that's probably the most, that's what string theorists normally take to be the strongest support for their theory. Now, one might, in principle, of course, also go up here. So the meta-inductive argument just looking at successful explanatory interconnection, but given so I don't think that, I mean, that's formally the last option, but I don't think it is a quite helpful option. I couldn't think of any actual case where this needs to be applied. So what one has here, and once again, still we are now in the context of empirical confirmation. We have a new general perspective on confirmation, where empirical confirmation actually has two components. It has the component of the agreement between data and the theory's predictions, which is represented by the probability of the evidence given the hypothesis. So it is one entry in the base formula. And we have the meta-empirical assessment that establishes a low value for the total probability P of E. And in order to extract values for the probability of the hypothesis given the evidence, you need to specify both. So you need to have both parts, or to be more precise, you definitely need to have the second part, right? So you need to be able to specify the probability of the evidence based on meta-empirical confirmation. We will come to the option that empirical confirmation is lacking, and it will turn out that we can still, in principle, can have successful updating in that case. So we can have successful updating just based on meta-level observations. Yes?
The term viability means a research program that deserves to be pursued.
The term viability means agreement with the data within a given empirical domain. So all the data that can be collected within a given empirical domain is in agreement with the theory's predictions. And yes, I didn't spell that out in detail. There is a reason why it is helpful to talk about viability here and not about truth. Canonically, the Bayesian would talk about truth, but truth, of course, addresses the global question, right? So when we distinguish between the global and the local question, if I ask whether a theory is probably true, I ask saying that the theory is true amounts to saying that there are no unconceived alternatives that anywhere contradict the theory. So that would be a global question. And this is normally not the way scientific reasoning about the theory status proceeds. So one wouldn't want to make such strong statements that would amount to final theory claims about a theory. One would just want to make statements about the viability of a theory, so the agreement of a theory's prediction with the data within a certain domain. And the concept of viability allows for making local claims. Yes?
Thank you. Another question. Why you choose this term, meta-empirical assessment, if in a certain sense, even this kind of assessment is empirical? Perhaps it would be better than like meta-theoretical assessment. That this is something that is beyond a certain theory, but it concerns something other. Don't know.
Yes, I mean, there is this question of the optimal terminology, definitely, there are pros and cons with respect to all of those formulations. I would say it is meta-empirical. So on this definition, empirical evidence is evidence covers observations that are in the theory's intended domain. Meta-empirical observations are observations that are relevant for the meta-level assessment. So they play the role of evidence at the level of testing the meta-level hypothesis, the hypothesis on the number of alternatives. But in some sense they are empirical, right. Yes. Okay. So now if one wants to spell out what has happened so far in terms of some diagrams, one might start with what I would call the naive understanding or the simple understanding of empirical confirmation. And that understanding would be that confirmation is about the theory predicting empirical data and then being empirically confirmed if there is agreement with those, between the data and those predictions. As we have seen when analyzing the structure of the base formula, that's just not enough. There is some important aspect of confirmation missing if I think about confirmation just in these terms, because this does not address the issue of the probability of the evidence, or in other words, the question of unconceived alternatives. In order to get hold of that, the probability of the evidence, one needs to make an assessment that allows us to make an estimate with respect to the number of unconceived alternatives and therefore the total probability of the evidence. And this plays out at the meta level, where I have this hypothesis about the number of unconceived alternatives that predict meta-level observations, the three ones that were spelled out. And if they agree, this leads to confirmation. So this, as already emphasized, this is a vague process that does not allow for statistical analysis itself. It is based on an estimate, but it can feed into this confirmation circle, because if updating on the evidence F, I infer a low number of unconceived alternatives, this increases the probability that my given theory is true, or is viable, sorry. So in the extreme case, if the hypothesis is there are no unconceived alternatives, then this implies that the probability that the theory is viable. If there, as would be normally, of course, the case, if the inference is not that dogmatic, I would still get an increase in probability. So the process of empirical confirmation would not work like this, but it works like this. So the increase of probability based on successful predictions runs via this meta-level assessment of the total probability. Now, the interesting case, and this now moves towards the issue of quantum gravity and the assessment of theories of quantum gravity. The interesting case in that respect is the case where we do have a meta-empirical assessment case, but there is no empirical confirmation. And it turns out that while without meta-empirical assessment there is no way of extracting credence in a theory, with respect to, let's say, the normal notion of conventional notion of empirical confirmation, this is not the case. So one should point out that this is a statement that relies on this canonical notion of empirical confirmation. So it means that not everything that amounts to empirically induced understanding of a theoretical situation counts as empirical confirmation. So if I would develop a theory in thin air without any connection to empirically confirmed theories, of course, the same would hold. I need both. But if I say, okay, I have these building blocks for quantum gravity, on the one hand, I don't know, I mean, let's say for string theory to be more specific, on the one hand, the empirically well-tested gauge field theories, on the other hand, the empirically well-tested theory of general relativity. I do have an empirical basis for developing the theory, but the characteristic predictions of the theory are not testable at this point. Yes?
So the question sort of connected to the previous slide. So
sorry.
you have published with Hartman and Sprander the paper on constructing the explicit Bayesian method for this no alternatives scenario, right? But then, like, there hasn't been like a follow-up of a paper which does sort of a similar thing, let's say, for unexpected explanation argument, right? So, I mean, I've tried to sort of think through that, attempting to see like what could be a proper Bayesian method. Like, I was always faced with this problem where when you try to construct like this sort of situation, like you have in here on this right side for unexpected explanation argument, you have this credence in theory T sort of blocking in Bayesian sense the connection between F and Y. Because if you have F, which is a meta-empirical evidence which says that, so yeah, maybe I'm getting a bit ahead of what's going to be the next lecture, but like, if you have the Bayesian confirmation, the meta-empirical evidence which says that string theory unexpectedly explains black hole entropy, then it will sort of, and then you have the theory T, like a statement, string theory is the empirically or like viable or true or whatever. It will block the confirmation path that goes to like the number of unconcealed alternatives, right? So yeah, I mean maybe we
can you? I don't think I fully followed your reasoning.
I mean, if like we try to construct the Bayesian model,
Yes. Yeah.
like it will not look like this for unexpected explanation. I mean, from the best I could try, because again, if the theory, string theory, is empirically true,
Yeah.
then the fact that it unexpectedly explains the black hole entropy will not affect the number of unconcealed alternatives. But if it's false, then it will also not affect the unconcealed alternatives, which then implies that it, like in the Bayesian sense, blocks this sort of path of confirmation which exists in this graph.
I don't think that that's the case, because if you conditionalize on either on those, it's right that you conditionalize either on truth or on falsity, you lose the significance. That's absolutely right. But if you don't conditionalize on it, so if you say that there is a certain probability of being viable, then it changes this probability. So that would be the mechanism. So in all those cases, if you conditionalize on viability or non-viability, you break the connection because you know already, so to say. So there still will be either alternatives or no alternatives, but the unexpected explanation will arise because the theory is true. You know that already, right? But so you don't want to do that for sure. So you must not start, let's say, by conditionalizing on the theory's viability, but you need to enter with the probability.
But this, like, I meant as a definition of conditional independence.
Yeah.
So, as a definition of conditional independence, this fact that specifically knowing the empirical adequacy of the string theory blocks this sort of confirmation path. It's a definition of conditional independence, and therefore it sort of just blocks this fact. I mean, like, I can ask you later.
Yes, maybe we can discuss in more detail later on. Yes, but what I want to say is that indeed, so just responding generally to your question. So it's right that the formal the formal proof of confirmation value has been developed with respect to an alternatives argument. We did, or I wrote a paper focusing on the meta-inductive argument that is not focusing on the proof of confirmation value, because that's fairly straightforward in the meta-inductive case, but it focuses on understanding the significance of meta-inductive reasoning in connection with an alternatives argument. And so that also works. You're absolutely right that the role of the formalization of the unexpected explanation argument has not happened yet, and there are intricacies. So there are issues with respect to how to do this. So it's not a yes. It is. There are issues with how to set this up. Yes.
Just briefly, like, I think the main difference between the alternatives argument and the unexpected explanation argument is that in the unexpected explanation argument, the meta-empirical evidence F is connected to a specific theory that you're dealing with. And in this case, you say string theory unexpectedly explains that black hole entropy. While in the alternatives argument, your meta-empirical evidence is not connected to a specific theory. You're saying, like, there's been just like one theory that's been found. And it, like, from what I try to think through, it does affect this conclusion.
Yeah, let's talk about this in detail later on. Yes, so starting from here and now moving towards this application to the case of lack of empirical evidence, what now plays the role of empirical data are requirements on the theory, constraints on the way the theory can be built that is based on the theory it aims to unify. So there is, of course, empirical. So there is empirical data that informs those theories that should be unified. So that it's not empirically it's not unconnected to empirical data, these requirements, but they are requirements that don't amount to empirical testing of that theory specifically. So they are at the more conceptual level, and of course in the case of string theory, this is particularly important because the string theory does not connect to the specific way low energy physics plays out. So it cannot be established, for example, that the standard model is a solution of string theory. So the connection to these, or the status of those requirements is really based on quite general considerations, such as the effective theory should be a gauge field theory, things like that. If one has these requirements in a similar way to what happened before can put constraints on the options of theory building. So the same process in principle can play out as in the case of where there is empirical confirmation of the given theory. So I can once again observe that, for example, no theories have been found that satisfy those constraints, those requirements that we have put up for building such a theory. And then the same circle can play out without reference to actual empirical confirmation of the given theory, and I can once again increase probability. However, this then, of course, only plays out if you think back to this diagram in those two boxes here. So there is no access to this box because we don't have empirical confirmation. Yes, so this is the idea. The upshot of the idea is that actually this process, the process of including meta-empirical assessment in understanding confirmation, is already essential to understanding a Bayesian account of empirical confirmation. And the additional step is just to say this process works also, even though in a weaker way only. It can work under specific conditions also if I don't have empirical testing of the theory, but I just have requirements that come from the unificatory task, for example, or the task of consistent representation of these individual low energy theories. All right.